We're asked to consider the function f of x comma y over the region defined here, which is a triangular region graphed here in the xy coordinate plane. Let's write the equation that would contain each of these boundaries. Notice how the equation y equals 0 would contain this side of the triangle. The equation x equals 4 would contain this side. And notice how the line y equals x would contain this side of the triangle. This would be on the line with a y-intercept of 0 and a slope of 1. We're asked to evaluate the double integral over the region D of f of x comma y. Before we do this though, let's look at the graph of f of x comma y over this region. The surface f of x comma y is graphed in blue. The xy plane is graphed in yellow. If we look down on the region of integration, which is this triangular region here, notice how we can tell if the surface is above the xy plane over this region, which means the double integral is going to be equal to the volume of the solid below the surface and above the xy plane over this triangular region. So going back to our work, let's begin by setting up the double integral. So the integrand function is y times the square root of the quantity x cubed plus 1. The given double integral has us integrating with respect to x first, then with respect to y. Because we integrate with respect to x first, we're integrating from left to right along the coordinate plane. So notice how the left boundary is going to be here along the line y equals x. The right boundary is going to be here, x equals 4. So we need to express the limits of integration with respect to x as functions of y. So because x equals y, y is the lower limit of integration, and the upper limit of integration is going to be x equals 4. And now with respect to y, we're going to integrate from y equals 0 all the way up to this high point where y is equal to 4. So with respect to y, we integrate from 0 to 4. If we leave the order of integration in this form, notice how we need to integrate with respect to x first, treating y as a constant, but it's going to be quite challenging to find the antiderivative with respect to x because we have the square root of the quantity x cubed plus 1. So for this example, let's go ahead and change the order of integration. So the integrand function is going to stay the same, but let's integrate with respect to y first, and then x. So if we integrate with respect to y first, notice how the lower boundary is going to be the line y equals 0, and the upper boundary is going to be this line here, where y equals x. Which means the lower limit of integration is going to be 0. The upper limit of integration is going to be x because y is equal to x. Integrating with respect to x, notice how the leftmost point is here where x equals 0. So we're going to start integrating at x equals 0 and stop integrating here at x equals 4. So with respect to x, we integrate from 0 to 4. Now let's go and evaluate this on the next slide. Integrate with respect to y, treating x as a constant, we're just going to have y squared divided by 2 times the square root of the quantity x to the third plus 1. And I'm going to write the square root as a rational exponent, so we'll have times the quantity x to the third plus 1 to the 1/2. Now these are limits of integration for y, so substitute x for y, then 0 for y, and then find the difference. And let's go ahead and factor out the 1/2, so we'd have 1/2 times the quantity. So when y is equal to x, we'd have x squared times the quantity x to the third plus 1 to the 1/2 minus, when y is 0, we'd have 0 squared times the quantity x to the third plus 1 to the 1/2. So of course this is going to be 0. So we have 1/2 times the integral from 0 to 4 of x squared times the quantity x to the third plus 1 to the 1/2 dx. Notice here we do have to perform u substitution, so we'll let u be equal to x to the third plus 1. So differential u is going to be 3x squared dx. Notice that we have x squared dx, so let's go ahead and divide both sides by 3. So we have 1/3 du is equal to x squared dx. So in terms of u, all of this would be, again, x squared dx is equal to 1/3 du. And because u is equal to x cubed plus 1, this would be u to the 1/2. So we'd have 1/2 times, with respect to u, we'd have 1/3 times u to the 3/2, and then instead of dividing by 3/2 times 2/3. So with respect to x, we would have 1/3 times u to the 3/2 would really be the quantity x to the third plus 1 to the 3/2. Instead of dividing by 3/2, we multiply by 2/3. Let's go ahead and clean this up a little bit. 1/2 times 1/3 times 2/3 would be equal to 1/9. So we have 1/9, and here we just have the quantity x to the third plus 1 to the 3/2, which we now need to evaluate at 4 and 0 and then find the difference. So when x is 4, we'd have 4 cubed plus 1 to the 3/2 minus, when x is 0, we'd have 0 cubed plus 1 to the 3/2. So we'd have 1/9 times, here we're going to have 4 to the third is 64, 64 plus 1 is 65, so we have 65 to the 3/2 minus, this would be 1 to the 3/2, which is just equal to 1. So this would be the exact value. Let's get a decimal approximation using the calculator. We have 1/9 times the quantity 65 raised to the power of 3/2, right arrow, minus 1, close parenthesis, and enter, which would be approximately 58.1163. And of course, we could label this cubic units because it does represent the volume under the surface above the xy plane over the region of integration, which again would be the volume of this solid in here. Okay, I hope you found this helpful.